This course is on probability. It's an introduction to probability, so we're going to hit the key concepts and make sure that you walk away with a decent understanding of the fundamentals of probability. We're going to first start off with probability, counting, and some axioms. And so let's first talk about some basics of probability. And so sample spaces and events. And so sample spaces and events are like the fundamental bedrock of talking about things probabilistically. So a sample space is going to be the set of all possible outcomes of an experiment. And so let's imagine you're rolling a die, right? A die has 6 different sides. If you roll a die one time, there's only 6 different possible outcomes. And so you can only land on 1, 2, 3, 4, 5, or 6. And so the sample space for rolling one die is going to be 6 different possible outcomes. An event, on the other hand, is a subset of the sample space, and it's a specific outcome or a group of outcomes. And so an event could be, for example, an event could be you rolling a 1, and so there's only one different possible outcome where that can occur. Or an event could also be the event that you roll an even number when you roll a die. And you can roll a 2, 4, or 6. And so 2, 4, or 6 would be a subset of those outcomes, and those would be an event. So a simple example is flipping a fair coin. Let's just say that we have a fair coin. We know that a coin can land on heads or it can land on tails. That's the only 2 possible outcomes. And so the sample space is heads and tails, right? So it's those 2 outcomes. And if we're interested in the outcome of getting a head, right, the event for that, we can call it event A, is going to be heads, right? So we flip a fair coin once. One event can be at getting a head, and another event could be at getting tails, and heads and tails makes up the entire sample space. And so why do we care about this? Well, I think when you get deeper into probability, having a clear understanding of what your sample space is, what are all the different possible outcomes of a particular experiment, or it could be a decision, and having an idea of what exactly the events are within that space, having that well defined, is going to be crucial to not only understanding probability theory in a course setting, but being able to apply space. We gave an example of flipping a fair coin. And now let's talk about the counting portion. So counting, the 2 main concepts here, and we're going to talk about them in their most fundamental form, are permutations and combinations. And so a permutation, so what are the differences between these 2? A permutation of a particular set of objects is a shuffling. You can just think of it as a shuffling of the ordering of those objects. So we care about the order. And a combination of those objects can be is more so expressed as a subset of those objects. What do I mean by that? So if I want to know what is a combination of 2 objects out of a set of 3, that would be any 2 objects, right, out of that set of 3 that are distinct. And so permutations, when we do a permutation, we care about the distinctness on the order of the objects we select. And in this case, we're only going to talk about permuting all the objects in our set. For a combination, we're only going to care about the distinctness of the objects themselves. And we are going to talk about subsets. And we don't care about the order, we just care about the objects are distinct. So let's move into a concrete example really quickly so we can make all of that make sense. Let's imagine that we have 3 objects. We have 3 characters. We have the letter A, we have the letter B, and we have the letter C. And those are our 3 objects. If I wanted to see all different possible permutations of them, this is all different possible permutations. There's 6 of them. You cannot do any more than these. And the only thing that is distinct between each one of these permutations is the order in which the characters come in. And so A, B, and C is different than A, C, and B because we have B and C flopped. And BAC is different than BCA because we have A and C flopped. And they're all obviously different than the first 2. And so that's what I mean by it's distinct on the ordering. And we're going to include, in our case, we're going to include all of the objects that we have, A, B, and C, in each one of our permutations. And now a combination is different. Because if I wanted to see what are all the different possible combinations that I can make of A, B, and C that are of size 3, that means I have to include every single object in each combination. There's only one combination. It's A, B, and C. There is no other way that we can create a combination of size 3 using A, B, and C, using all the characters and all the objects, without it actually being a duplicate. And so, but we can talk about combinations in terms of subsets. What are all the different possible combinations of A, B, and C of size 2? You can imagine it could be A and C, B and C, A and B. And so we have formulas for calculating these things. We have the number of permutations. In our case, we're talking about the simplest form. You take the number of objects you have. We have 3 here, and you calculate the factorial of that. So if you have n equals 3 in our case, the number of permutations is going to be 3 factorial. 3 factorial is 3 times 2 times 1, which is equal to 6. And so that's how you compute a factorial. So if you have 7 objects, you compute 7 factorial. It's the number of permutations, and it would just be 7 times 6 times 5, all the way down to 1. The number of combinations, we express them as a subset. So if we have n objects in our case, we have 3, and we wanted to see all the different possible combinations of size 3, it'd be C of n equal to 3, R equal to 3, and then you would just plug those numbers into this formula. It'll tell you all the different combinations you can make of that size. If we wanted to see all the different combinations we can make of n equals 3 objects or n equals n objects of size 2, we would plug in n equals whatever our n is, be 3 in our case, and R equal to 2, and then that will tell me all the different combinations of size 2 out of these 3 objects that I can make. And so these are going to be important when we talk about the birthday problem, where we literally have to compute this ourselves. And it's going to be important throughout probability. Okay, so let's talk briefly about some axioms of probability that I think are pretty important to understand. It won't take long. But first and foremost, we talked about a sample space, and we talked about events within that sample space. Non-negativity is the first thing. If there is an event in a sample space, the probability of that event happening has to be greater than or equal to 0. It cannot be negative. Unit measure. And so if we look at all the events in a sample space, remember we had a die. Let's just say we had a die, and we rolled it, and we looked at all the outcomes of that, of one single roll. We had 1, 2, 3, 4, 5, 6. Those are all the events in the sample space, is the entire sample space. The sum of all of their probabilities is equal to 1. So all the probabilities of all the outcomes in a sample, all the outcomes of an experiment, or all the events in a sample space, should be equal to 1. Now, additivity. So if we have 2 events in a sample space that most certainly cannot occur at the same time, they cannot happen together. For example, if you're flipping a fair coin, you cannot get heads and tails at the same time if you flip it once. That's impossible. And so the probability of heads happening is 0.5 because it's 1 over 2, and then the probability of tails happening is 1 over 2 as well. And so the sum of all the probabilities is going to be the sum of heads plus the sum of tails, which is going to be 1. And that makes sense for our unit measure law because that's the entire sample space is heads and tails, and it sums up to equal to 1. And they're mutually exclusive. They can't happen at the same time, and so we sum up each of their probabilities. We have other rules too, like the complementary rule, which says that the probability of an event not happening is just going to be 1 minus the probability of that event happening. So if the probability of tails not happening when we flip a coin that's what we care about calculating, it's just going to be 1 minus the probability of tails actually happening, which is going to be 1 minus 0.5 or 1 minus 1/2, which is going to be 1/2. And so now we have the addition rule, which says that the probability of 2 events happening is just going to be equal to the sum of the first one, the probability of the first one plus the probability of the second one, minus the probability of their intersection. And so we're going to subtract off their intersection because we don't want to double count it when we're calculating the probability of both of these events happening. And so I think right now we need a visual understanding of this because this is something that requires thinking about probability in terms of sets. And so let's head over to a more visual explanation of this. And so I have our addition rule right here. And so I want to draw our sample space. An example is sample space, and this is how they're commonly drawn. And then we're going to, with a little omega sign, just say it's a sample space. And let's just say that in this sample space, all these little dots represent a possible outcome of an experiment. And let's just say that I have defined these group of dots over here as being the event A. All these outcomes are the event A. And then this over here is all the events, or all the outcomes that I would say occur in the event B. And now, what this rule says is that if we want to know the probability of every single one of these little dots that are in A and B happening, all these different outcomes, we want to know the probability of all of them happening, what we can do is we can sum up everything, the probabilities of all these outcomes happening in A, right? And then we can sum up all the probabilities of all of these outcomes happening in the event B. And then what we need to do now is we need to subtract off this intersection, because maybe I didn't draw it to perfection, but this intersection was counted twice. And what we do is we subtract that off because we only want to count that one outcome right here, this one outcome. We only want to count it once, because what we're just trying to get is the sum of the probabilities of all the outcomes. And so that is what I wanted to explain this rule. And not only that, you got a visual understanding of what a sample space is, how to review them in a set theoretic sense. You know, all these dots are outcomes. This is what an event group would look like, or an event would look like, sorry. And then this is what an event was. And then this is why we subtract off that intersection so that we don't count that one outcome twice. So in this video, I want to talk about the birthday problem. So the birthday problem, or the birthday paradox, is a famous problem in probability, and it states that it's kind of counterintuitive. It states that in just a group of 23 people, all you need is 23 people, that there's a 50% chance that at least 2 of those people share the same birthday. And so you got to think, there's a lot of birthdays out. These 365 days in the year, there's a lot of birthdays, and you tell me that all I need is 23 people in a room, and there's a 50% chance, a coin flip of a chance, that at least 2 of them share the same birthday. And so how does this math work? So it essentially says that the probability of 2 people having a different birthday, right? We have the start here. The probability that 2 people have a different birthday is 364 out of 365. You know, there's 364 days in a year other than the day of the first person's birthday. And so in a group of 23 people, there are 253 possible pairs, using the formula for number of combinations of size 2, because we're talking about pairs of people. Essentially what we do, moving on to the next slide, is that we know that the chance that they have a different birthday is 364 out of 365. We know that there's 253 possible pairs. And we're trying to say, first we find out what's the probability that all of them have a different birthday. Every single pair of people out of 253 have a different birthday. Well, that's the same. How we can calculate that is, let's imagine that we flipped a coin that had a 364 out of 365 chance of landing on heads, and a 1 out of 365 chance of landing on tails. Well, to get the number of times that coin is going to wind up being on heads every single time we flip it, is going to be 364 out of 365 raised to the number of times we flip it. And since we're flipping it for each single pair, there's going to be that number raised to 253. And that number winds up being 0.4995. And 0.4995 is a probability that every single pair out of all the different possible pairs has a different birthday. And so if we wanted to get the probability that at least one of those pairs has the same birthday, it's just going to be 1 minus the probability that none of them have the same birthday. And so that's why we do 1 minus that probability, and we get 0.5005, or a 50.05% chance that at least 2 people share a birthday in a group of 23 people. And this right here is a general formula for n people. You can get the probability of any given pair, at least one pair, having the same birthday by just plugging n into this formula, differing values of n. So let's move into a more visual example so we can start breaking down different parts of this problem. Let's first start with this 364 out of 365 probability that not birthday means not the same birthday between any 2 people. Why is that the case? Well, if 2 people, right, I'm going to draw my 6 figures here, do not have the same birthday, I'm just going to do the equal sign. do not have the same birthday, and I'm just going to use the not equal sign. Okay, 364 out of 365. Why does this make sense? Well, let's think about this. If there's a 364 out of 365 chance they don't have the same birthday, there's a 1 over 365 that it's the same. And why is that? Well, let's think about this. Let's shrink this problem down, and let's assume that we had only 6 outcomes. Let's say that 2 people rolled a die. Let's say that 2 people rolled a die. So this person rolls a die on one side, and then the other person rolls a die on their side. And I'm trying to calculate what is the probability that these 2 people roll the same. And so there's 6 outcomes here. There's 6 outcomes here. This is going to be person number 1, and then this right here on this top portion of this column is going to be person number 2. And so this is going to be our table. Oops, sorry. And so let's imagine, okay, that so how you could read this is that person 1, let's say person 1 rolls a 5, okay? That means person 1 is in this row, and let's just say person 2 rolls a 6. So that means that this right here is going to be where I would leave my check mark for that one. So there's 36 possible outcomes here. Person 1 can roll a 6, and then person 2 can roll a 4, and that's one possible outcome. Person 1 can roll a 3, and then person 2 can roll a 5, and that would leave us over here. Person 1 can roll a 1, and person 2 could roll a 1, and it'll land us right here. And so the probability, though, that these 2 people roll the same number, if person 1 rolls the die and person 2 rolls the die, the probability that they roll the same number, well, it's just going to be the number of possible outcomes in our sample space. This is our sample space, which is just all these on the diagonal, where person 1 rolls a 6 and person 2 rolls a 6. Okay, it's going to be all of these possible outcomes divided by all the possible outcomes in the entire sample space. And so there's 6 check marks here. There's 36 little squares. And so the probability of them rolling the same number is going to be 1 over 6. And so now let's blow this up to be 365 here and then 365 here. There's only going to be check marks all the way along the diagonals. And so there's going to be 365 check marks, just like there was 6 here, divided by 365 squared outcomes. And that, if you do the math, winds up being 1 over 365, that they have the same birthday, and 364 over 365, that they don't have the same birthday. And so that's why 364 out of 365 makes sense. Let's talk about the number of pairs. Why does that make sense? Well, we know that the formula for calculating the number of combinations is going to be this. We did R. You don't have to do R. You commonly will see K. And so what we want to know, okay, is we have 23, we have 23 people, and we want to know how many different combinations we can create out of 23 people of size 2, because we're trying to get the probability that any 2 people have the same birthday. Well, that's going to be 23 factorial divided by 2 factorial times 23 minus 2 factorial, which is going to be 21 factorial. And now you're probably thinking, how do we get 23 times 22 divided by 2? Go back to that slide if you don't remember that. Well, think about it this way. The one thing about these factorials is these are big numbers, but we know that 23 factorial is going to be 23 times 22 times 21 times 20 and so on. But really, we can cut this off and say that this is 23 times 22 times 21 factorial, because we know that this remainder is going to be 21 factorial. And we know that down here, we still have 2 factorial and we still have 21 factorial. Well, these cancel out just because of algebra. And then we have 23 times 22 over 2 factorial, which is just 2 times 1, which is 2. And then this is how we get our 23 times 22 divided by 2. And we do this, and we're going to get 253 possible pairs. Now, that is how we got the number of pairs. We know how they came up with 364 or 365 by this example. We now know how they came up with how many different combinations of people, or pairs in our case. And so we need to put this together into figuring out how they came up with this 50% number. Well, we do know that the probability of not same, okay, it's going to be 364 over 365. We know how many trials slash pairs. Let me write that a little bit more clearly. We know how many trials slash pairs we have. We have 253. Okay, so let's simplify this real quick, and let's imagine that we're talking about a coin flip. If we're talking about a coin flip, and let's just say that we're flipping a coin, a fair coin, and we know that the probabilities of getting heads is 0.5. Well, let's just say that the number of trials that we cared about is equal to 3. And I wanted to know, what is the probability that we're going to get all heads? If I flip a coin 3 times in a row, what's the probability that all of them land up heads? Like head, head, head. Well, we know on the first try, right, the probability of us getting a heads is 0.5. We know on the second trial, it has nothing to do with what we had on the first trial. The coin is completely random. And so we have 0.5 here as well. And so on the third trial, it's going to be the same thing. And then if we multiply this out, this will give us the probability that we get all heads when we flip a coin 3 times, that all of them land up heads. 0.5 times 0.5 is 0.25. 0.25 times 0.5 is 0.125. And so here, what we're saying is that, okay, this is the probability of getting all heads. And so what's the probability of getting just one tail? One tail. This is going to be every other outcome that could possibly happen in this 3 flip sequence right here. Every other possible outcome includes a head. And so getting greater than or equal to one tail is just 1 minus this. Okay? And so that's going to be our answer for this problem. And so over here, we're trying to get what is the probability that we can at least one pair of people. Okay, that's what we're trying to ask now to relate this over. What is the probability that at least one pair out of all these pairs has the same birthday, right? Greater than or equal to one pair has the same birthday. Well, it's going to be the same formula. We're going to take 364, okay, over 365. We're going to raise this to 253. And then we're going to take 1 minus that, and that is going to give, in this, oh wait, so let's backtrack. This right here is going to give us the probability that every single pair has a different birthday. And then if we want to figure out what is the probability that at least one of those pairs has a birthday, we would just subtract that number off to get the number that we got beforehand. And so this right here is the probability that at least one of those pairs, it could be 1, 2, 3, or 4, but at least one of those pairs has the same birthday. And so that's sort of breaking down the logic of the birthday problem and how it actually works. And hopefully you gain something from that in terms of understanding, one, if we go back up all the way over here, what it really means to have 1 out of 365 chance of having the same birthday between 2 people. By understanding a sample space and all the different possible outcomes, we understand how to use the combinations formula, and even talked about a little algebra that you would use a lot if you use this formula. And then we talked about this and related it back to a coin flip and try to figure out, what does this really mean to have at least one pair that has the same birthday. So conditional probability and independence are really important concepts, especially when you get to start applying probability to the real world. So what is conditional probability? Essentially, we're trying to answer the question of what is the probability of an event A happening given that an event B has already occurred. And so you probably ask yourself this question a lot. What is the probability of this specific thing happening or something happening given that we already know that this has happened, right? When we start conditioning on other information, the probability of an event happening changes quite a bit. And so the formula for it is going to be the probability of A given that B happened is going to be equal to the probability of A and B happening at the same time divided by the probability that B happened. And so, like I said, this is where both events have occurred, and then we divide by the probability of B happening. Now, this is if the events are not, independent. They're dependent on each other in some way, shape, or form. If A and B are independent, like if A is the probability of getting a heads and B is the probability of getting a tail, the probability of getting a heads does not change given that tails just happened. If we flip the coin twice, we just saw in the birthday problem example, if we flip a coin twice, the probability, if we get heads on the first flip, the probability of us getting heads or tails on the second flip, given that the first one was heads, is still 0.5 because the two flips are completely independent. And so if two events are completely independent, the probability of one happening, given that the other happened, is just going to be the probability of that event. So the probability of A given B is now just the probability of A. So let's start with a really simple example. Let's imagine that we have 52 cards. We have a deck of cards, and we have 52 cards in that deck, and we want to be able to answer the question of what is the probability that a card is a king, given that the card is a heart. And so event A is going to be that it's a king, and event B is going to be that the card is a heart. So the probability that a given card is a king, given that it is a heart, is going to be the probability that it's a king and a heart, divided by the probability that it is a heart, that a card is a heart. Now, in a deck of 52 cards, 13 of them, it's evenly distributed across all different types of cards, but we know that 13 out of those 52 are going to be hearts. And so the probability that a card is a heart is 13 out of 52. Now, the probability that a card is a king and a heart is 1 out of 52 because there's only one king of hearts in a deck of 52 cards. And so we divide these two numbers by themselves and we get 1 out of 13. And that should make sense because if we already know that we're in the set of these 13 cards that are hearts, how many of those are actually kings? There's only one. And so I think let's hop into a visual example real quick to get a decent understanding of what this means, and so we can help visualize it in our heads. And so we're trying to answer this. What is the probability of a king given, and I'm going to draw a heart, that the card is a heart, right? And we're saying, well, this is going to be the probability of getting a king, and that's going to be my intersection sign, and a heart, divided by the probability that a card is even a heart. Well, we said that this is going to be 1 out of 52 because only one of those exists in the deck, divided by, right here, this is going to be 13 over 52. And we came away with 1 over 13. And I said this makes sense because visually speaking, if we look at our sample space right here is going to be all the different types of cards. If we think about this, if I divide this region into 4 regions because there's 4 different types of cards, this region right here is going to be all the different types of hearts. And we know that there's 13 hearts. So I'm going to draw 4, 5, 13 hearts. 1, 2, 3, 4. And then here we have like an ace, and then we have a king, and then we have a queen. And we know that our king is right here. Our king of hearts is right here. It's got this sliver. We know that there's 13 of these, and so we know that we're already here. We are nowhere else. We're in these 13 cards. And that king is one of those 13. And so that's why it's a 1 over 13 probability that a card is a king if it is a heart. And so because there's only 13 hearts and only one of those hearts is a king. And so I want to talk about Bayes' theorem. Bayes' theorem is another way of thinking about conditional probabilities. What is the probability of something happening given that we now know that something else happened? It was created by Thomas Bayes. I believe it was created post mortem, to where the Bayes' theorem wasn't actually developed or discovered until after Thomas Bayes had passed away. I believe some papers were found that he left behind that never showed anyone. It's a quite interesting story. Please look it up online if you feel free to do that sort of thing. But essentially, it relates these probabilities, right? The probability of A given B happened. It relates that probability to the probability that B happened given A happened, right? And it uses this formula, right? it's the probability of A given B is going to be it's going to be equal to the probability that B would happen given that A happened times the probability that A would happen in the first place, all divided. Everything here is divided by the probability that B would occur. Now, let's break this thing up a little bit, right? So the probability that A given B is that right here, probability of A given B, is the probability of A happening given that B has occurred, right? So we understand that from conditional probability. But let's move forward. The probability that B happens given that A has occurred, well, that's the opposite. And you can read it exactly like that. And this is called the likelihood. So you'll commonly see this referred to as the likelihood. So now we have the probability of A, right? So the probability of A, remember the numerator was the probability of A times the probability of B given A. The probability of A is the probability of A occurring, and it's also known as the prior probability. We're supposed to elicit, Bayes' theorem is subjective, and we're supposed to elicit our prior probability that A has occurred. It could be based off some data that we had collected on the event A. It could literally just be based off of our opinion. That's the powerful thing, is that now we're talking about conditional probabilities in terms of subjective belief. What is my prior probability that A is going to occur? And B is going to be the probability of event B occurring. And so Bayes' theorem allows us to update our belief in A occurring, given that we've taken in some new evidence on event B. So, and it allows us to continuously update that belief on A, given that we collect new data. And that's why Bayes' theorem allows you to have this idea of subjectivity. You know, we're allowed to elicit our prior probability on A. Say we know nothing about A occurring and we say it's a 25% chance that it'll happen. Well, we just collected some data on B, right? And so let's update that belief, and maybe that probability will go down by a little bit, or maybe it'll go up to 30% that A has occurred given that we collected this new data. And then now on our next experiment, we're going to say that our prior probability that A has occurred is going to be 30% if it went up. We're going to take that new posterior probability is what it's called, and use it as our new prior probability in the next experiment. And so I'm going to show you how this actually happens through a concrete example. And so I have some information already written on the board because I don't want you to see like all the math that went into it. I just want to explain it to you, and I even have some step-by-step solutions here. But essentially, let's use Bayes' theorem to answer this question. Let's imagine that you have a friend that's about to play a gambling game with you, and maybe it's just for fun. And they're like, okay, what we're going to do is that if I get a certain number of heads, let's just say that we're going to flip a coin 10 times, and if they get a certain number of heads, then they win, some money. And then if you get a certain number of tails, then you win some money, right? And so the whole idea of this game is that you want tails to happen more than heads, and they want heads to happen more than tails. And so if this is your friend, right, maybe you trust them a little bit, but not all the way, especially when it comes in terms of this. Maybe you want to know, hey, what is the probability that this coin is loaded, right? Like, what's the chances that this coin is even fair or loaded? Because it could be that they brought me a loaded coin and now they want to place a bet with me and they're going to get all these heads and then I'm going to lose my money. And this is a theoretical example, but let's imagine we had some information about it. And so you're a little apprehensive about whether it's fair or loaded. And so you ask them to flip the coin one time just to see what it lands on, just to get a feel for it. And let's just say that it came up heads. And now you're trying to figure out what is the probability that this coin is fair, which we've defined as the event A, given that the coin came up heads, which we define as the event B. And so now we're going to use Bayes' theorem. And how are we going to use that? Well, let's imagine that these are our priors. And these are just based off subjective belief. And let's just say that we're going to give our friend the benefit of the doubt, and we're going to say that the probability that this coin is fair is 0.6, which is a little bit higher than the probability that it's not fair, which is 0.4. And these have to add up to 1 for this to be a proper probabilistic statement. And so those are your probabilities. Maybe you have a little bit more trust in your friend that they brought you a fair coin, and they just want to have fun. Well, here's the thing. So here's the likelihoods, right? So let's assume, okay, that we're in this state where the coin is fair. Well, if the coin is fair, the probability that it comes up heads, given that it is fair, is going to be 0.5. We know that fair coins come up heads 50% of the time. Now let's imagine, let's switch over here to where it's loaded. And this is something that we came up with for the sake of this experiment right here, this lesson. Let's just say that the probability that a coin's going to come up heads if it is loaded, so this is heads, given that it is loaded, right, is 0.7. It's going to come up heads 70% of the time if it's a loaded coin. And this is what this means right here, the probability of heads given that it's loaded is 0.7. So we have our priors, we have our likelihood. And now if we remember Bayes' formula, right, Bayes' formula is this: the probability of A given B, okay, is going to be equal to the probability of A times the probability of B given A, right, divided by the probability of B. Well, we know these and we know these. What we want to do is we want to figure out this. And this is commonly known as our normalizing constant. And the probability of B happening, the probability of us getting a heads, given that we have these priors and we have this likelihood right here, is going to be, let me move this down just a little bit, is going to be a weighted average. All right, we're going to take the probability that it's a heads, right? The probability that it's fair, and we're going to multiply that by the probability that it shows up heads, given that it's fair. Because we're just trying to figure out what is the probability that it's heads. We're just trying to figure out the probability of B in our formula right here. And so we take the probability that it's fair times the probability that it's heads if it's fair, added to it the probability that's not fair times the probability that's heads if it's not fair, and we take a weighted average of our priors and our likelihood to come up with the probability that it's going to come up heads given our prior information. That's how probability of B is actually calculated. And so now what we need to do is we just need to plug all this in our equation. We know the probability that it is fair, our prior probability that it is fair, is 0.6, right? And we know that our probability that it's going to come up heads, if it is fair, right, is going to be 0.5, because a fair coin comes up heads 0.50% of the time. And then we have the prior probability, we have the probability of B, the probability that it's heads given our prior information. It's going to be 0.58. And this is going to be 0.3 divided by 0.58, which is going to be equal to approximately this right here, 0.52. It's actually going to be 0.5178. And now this right here is our updated probability that the coin is fair, right? And if you notice, it's lower than our original belief. Our original prior belief, we gave our friend the benefit of the doubt, and we said, okay, this is our friend. I at least hope that they're being, they're doing this the right way, and it's a fair coin. So we said there's a 60% chance that it's fair. We did all of our calculations, and then this friend, remember, this friend flipped the coin. Right? We had a 60% chance that the coin was fair. The friend flipped the coin and it came up heads. And now we go, whoa, we need to update our belief that this coin is fair. Because we know that a loaded coin comes up heads 70% of the time. And so we run our beliefs through Bayes' formula, Bayes' theorem, and we said, let's retract a little bit. I now believe that the probability of this coin is fair is actually about 52. Right, 0.52, 52% chance this coin is fair. And so we dropped our belief, right? And let's just say that our friend was to come up and flip the coin again. We said, flip it again, flip it again. And they flipped it again, and it came up heads again. We'd go, whoa, we need to drop our probability that it's fair again. And you would see this number continuously drop, where the next time we ran our, let's say the next time they flipped it, it came up heads. Our next probability, our next prior probability would not be 0.6 in our formula. It would be our previous probability that we calculated, which would be this one. And then we would continuously do that, plugging the posterior probability, is what it's called, that it's fair, as our prior probability in the next flip. And we would just continuously update that belief. And if your friend just kept on dropping heads, right, if they flipped it 7 times and it was heads every time, you would go, You would see the probability that it's fair go down pretty low, and that's how Bayes' theorem is used. You can elicit your prior beliefs into. So let's talk about discrete random variables. A discrete random variable is a random variable that only takes on a finite or countably infinite number of distinct values. We should be able to count the number of outcomes often associated with the outcomes of an experiment. And we've already talked about discrete random variables. We talked about two cases. The first example right here on the slide was rolling a six-sided die. The possible outcomes are 1, 2, 3, 4, 5, and 6, and that actually those outcomes and the experiment of rolling the die is the random variable. When we roll a die, when we roll a die, or this random variable x, it's going to produce 6 known outcomes, and we can count those outcomes. It's a finite set. It has a beginning and an ending. That's sort of how that's why it is a discrete random variable. And now flipping a coin is a discrete random variable because it only has 2 outcomes. It's finite, it's countable, and so flipping a coin is a discrete random variable. And now discrete random variables have what are called probability mass functions. It's a little bit different than continuous random variables, which we'll talk about later. And this mass function just maps the outcomes of an experiment of a discrete random variable to probabilities. And so this probability mass function will be able to tell you what is the probability of 1 occurring, a 2 occurring, or a 3 occurring. And so this is where we talk about the discrete probability distribution, or the probability mass function, the PMF. And it's going to take all those outcomes of a random variable or a random experiment, and it's going to map them to probabilities. And so in the example of a die, we had 6 different outcomes, 1, 2, 3, 4, 5, 6. This probability mass function is going to have, for each outcome, let's just say outcome number 1, it's going to map 1 to its probability of occurring, which is just 1 over 6 because a die is completely random. And so a probability mass function for a discrete random variable such as a die would have, for each outcome 1 through 6, it would have the probability 1 over 6 for each one of those outcomes. And to abide by the laws of probability, the sum of all the probabilities of all the outcomes in the PMF is going to be equal to 1. And so now I want to go through some examples of discrete random variables, talk about them more closely, and then discuss how we can compute some statistics on those random variables, such as the expected value and the variance. And so here's two examples. One is rolling a fair 6-sided die. So a fair 6-sided die, let's just say it's a random variable x, right? This represents the number after a die roll. And so x is going to be the experiment itself. And this experiment can produce 6 different possible outcomes, each with a probability of 1 over 6. And so the PMF for this, or the probability mass function of this distribution, is going to be represented as such. The probability that this random variable or this experiment is going to be equal to any little value x, right? X little x being 1, 2, 3, 4, 5, or 6, and then big X being the experiment itself. The probability that x is going to be equal to little x is going to be equal to 1 over 6 for every single one. They're equal probabilities all across. And that's going to be the same thing for if the random variable was flipping a coin, the outcome of flipping a coin, that experiment. It can only take on 2 possible values. Each value, heads or tails, has a probability 1 over 2 of occurring. We're familiar with that. And so the probability mass function for this is going to be the probability that this experiment of flipping a coin, x, this random variable x, is going to be equal to any little x, where little x can be h for heads or t for tails. It's going to be 1/2 for 0 or 1. You can represent 0 for tails or 1 for heads. It's just going to have it's literally the PMF just maps outcomes of a random variable to probabilities of that outcome happening for that random variable. And now let's talk about how to compute the expected value of a random variable. So first, what is the expected value? It's a measure of central tendency. You'll see it represented that way, but it's like the average outcome of a random variable, right? So the average outcome, if you were to, let's just say for a roll of a die, right? The expectation of that random variable, if you had rolled that die an infinite number of times, taken every single outcome over all those times, and then taken the average of it, that would be the expectation. And there's direct ways to calculate them for discrete random variables. We commonly denote them as e of x with this capital E. And it's literally what you do is you take every single possible outcome, like 1, 2, 3, 4, 5, 6 in our roll of the die scenario, and then you multiply it by its probability of x equal to little x, or the probability that that outcome occurs. And so this would be this, and you take the sum of all of them. So this would be 1 over 6 times 1 plus 1 over 6 times 2 plus 1 over 6 times 3, and so on until you get to 1 over 6 times 6, and you add them all up, and you would get an average of 3.5. And it ranges over all values of x. And we're going to see this in an example, so we're going to hop through this, and then we're going to see in a concrete example how this actually works out. So that was the expectation of a discrete random variable. The variance and standard deviation is a tad bit trickier, but it's just a measure of dispersion around the mean. If you had ran that roll of the die experiment, if you had rolled a die 1 time, 2 times, an infinite number of times, and you tracked the outcome for each experiment, the variance, the expectation is going to tell you if you had added them all up and then divided them by the number of times you ran that experiment, or you'd averaged them. The variance is going to tell you how much it varied from experiment to experiment. So you may have gotten a 1 on the first roll, a 3 on the second roll, a 6 on the next roll, a 5 on the roll after that, and it sort of bounces around. And that's what variance is going to calculate, to the extent to which it disperses around its mean and how much it jumps around. The variance is a little bit different. So instead of taking the expectation of x, right, the variance is going to be, what we're going to do is we're going to take every single possible outcome, 1, 2, 3 up to 6. We're going to, from each outcome, we're going to take it, we're going to subtract off the expectation of the original random variable, which is 3.5 in our case, and then we're going to square it. And so we're going to transform all the outcomes of the experiment by this inner portion, x, the outcome, minus the expectation of the entire random variable without transforming it, squared. And then once we have these outcomes squared, their values squared, their probabilities are still the same. And so we just calculate the expectation how we would do beforehand, probability times transformed outcome plus probability times transformed outcome, and so on. And that's going to be the variance. And don't worry, I'll show you an example how this works. The standard deviation is just the square root of that. So once we calculated the variance of the random variable, we're going to just take the square root of it, and that's going to give us the standard deviation. And these are just both two measures of dispersion. And so now what I think is good is for us to hop through an example on how to compute these on a simple example like rolling a die. So in this video, we're going to compute the expectation and the variance of a random variable x, which is the rolling a 6-sided die. And so our random variable x is going to be it's going to symbolize an experiment of rolling a 6-sided die. We know that this random variable can take on 6 different outcomes. 1, 2, 3, 4, 5, and then 6. And so first, let's really gain an understanding of what the PMF, or the probability mass function for this, looks like. We're going to have 1 here. On the x-axis, we're going to have the outcomes of our experiment. 4, 5, 6. And then on the y-axis, we're going to have their actual probabilities. But because we are dealing with an example like rolling a die, all of them are going to have probability 1 over 6. And I drew this halfway up. If this was probability 1 and this was probability 0, we'd probably be somewhere around here. 1 over 6. And then each one of these, I'm going to draw a little bar, a little line, to characterize the probabilities. Cool. And so all of these are the same. This is a rolling a fair die. You know, everything is the same because the experiment is completely random. First, let's compute the expectation. Awesome. And so the expectation is actually the most straightforward to calculate. It's just going to be, I'm going to write my E like this. It's going to be the expectation of x, right? It's just going to be, we know it's the sum of little x it's going to be the sum of little x times p of x, probability of little x occurring for all outcomes, right? And so this is going to be 1/6 times 1, the actual outcome 1, because we have a 1/6 probability of getting 1, plus a 1/6 probability of getting 2, and then so on, getting 2, and then so on, until we get down to a 1/6 chance of getting a 6. And if you do this math and you sum it all up, I won't do it here because it'll take too much time, or it'll just take extra time, you'll get a number that is 3.5. And this is the average. This is the expected outcome. If you were to take the average of, if you run this experiment an infinite number of times and then take the average of all those outcomes, you'd get 3.5. And so let's talk about the variance. How would we calculate the variance of this? So since we know the expectation. Well, the variance, okay, I can write that a little bit better. This is the formula for the variance. Expectation of x minus e of x squared. It's going to be the expectation of x minus the expectation of x squared. Okay, and so let's compute this inner part. Let's first write x minus e of x. And well, this is just going to be every single outcome minus the expectation. And so every single outcome, so the expectation of these numbers right here, we're going to transform every single outcome. So that's going to be, so 1, right, was 1 beforehand, but now we're going to take 1 minus 3.5, okay, squared. And then that's going to be our new 1, right? So it's going to be the transform 1, which is going to be negative 2.5 squared. What is negative 2.5 squared? It is 6.25. 6.25. And then that's our new 1, right? Well, we do it for 2 as well, so we have to transform 2. And so we subtract off 3.5, and then, which is 2.25. And then you would continue doing this, just transforming all the outcomes like you normally would. I won't do it here because you can already see this is taking a long time. But then once you have them, now you have a completely new probability mass function. What you have is now a mass function that looks, you now have these transformed values. And then that's going to be our new, that was our previous 1, right? And then this is going to be our new 2. This is our previous 2, right? And then so on, all the way up to our transformed 6, which we didn't calculate. They still have their same probabilities. They're still 1 over 6. And so that has not changed. And what you do is you now compute the expectation of this new transformed PMF, with the outcomes are transformed. And it's like 2.91 and some change. And so that would be the variance of the distribution. But I wanted to show you how that calculation works so that you can understand how to do it on your own. And hopefully that has helped you understand how to compute the variance of a discrete random variable, as well as the expected value. So now let's talk about continuous random variables. A continuous random variable is different than the discrete random variable, because a discrete random variable, like rolling a 6-sided die, can only take on a finite or countable set of values. Like the 6-sided die can take on values 1, 2, 3, 4, 5, 6. But the continuous random variable can take on an infinite number of values. And so, for example, it can take on values from negative infinity all the way to positive infinity. The normal distribution is a common example for a continuous random variable, because it can take on values from negative infinity all the way to positive infinity. It can even have a finite range, but inside of that range, it can take on an infinite number of values. For example, the discrete random variable for our six-sided die experiment can take on values between 1 and 6, but we can count those values. We can count 1, 2, 3, 4, 5, 6. The continuous counterpart for that would take on an infinite number of values between 1 and 6. So it can take on values like not only 2, but it could take on 2.00001, 2.0000011, 2.00002, things like that. And so it's on the real line, it's real numbers, and it's an infinite number, and that is why it's called continuous. The probability properties still stay the same. Every single outcome must have a probability greater than or equal to 0. The difference is that we now compute the statistics with integrals instead of summations. And so you don't have to be familiar with integral calculus to be able to follow along with what we're saying here. But essentially, an integral in this example, when we wanted to calculate the expected value of a distribution, the discrete random variable, we summed up the outcomes times their probabilities, right? An integral does that same thing, but it does it over an infinite range. And so it's a way for us to compute those summations for numbers that can take on infinite values. So the expectation of a discrete random variable is done using the integral instead of the summation property. You remember beforehand, we did the summation of the outcome times the probability of that outcome. Well, here we're doing the integral over each outcome times the actual density at that point, where f of x is a probability of that outcome under the distribution. And so we're dealing with densities now, right? We have a probability density function instead of a probability mass function, because now, and you can think of it this way, between any range of numbers, like think of the range of numbers 1 through 6, it now has so many values that it can take on, so many outcomes in between those that it can take on, that you're really talking about densities, because there's so many values within any specific range that a continuous random variable can take on. And so you're taking an integral over the outcomes times their densities or their probabilities. And the variance is calculated using the integral as well, because the variance requires the expectation, and the integral is used instead of the summation. And so it still measures the same thing, except we're using integrals instead of summations. And so I think this is a good point to step into an example of what does it really mean to have a density? What does it really mean to calculate the expectation of a random variable that has a probability density function? And so I think let's do that. So before we jump into a visual understanding of what the uniform distribution is in terms of a continuous probability distribution, let's go over some few characteristics of it. So we know that continuous random variables, they have probability density functions, not probability mass functions, because we deal in terms of densities because we're dealing with between any range of outcomes, say between A and B here, there's an infinite number of numbers in between that range, and so we deal with a density. And so the uniform distribution is going to be for any number x, for any point in any range of numbers, it's just going to be 1 over the difference between the end of the range and the beginning of the range of numbers that this random variable takes on. And so if a continuous uniform distribution takes on values between 1 and 10, right, and it takes on an infinite number of values between 1 and 10, it's at any given point between 1 and 10, it's going to take on the value 1 over 10 minus 1, which is 1 over 9. And so this is how we calculate the expectation and the variance of a uniform distribution. It's just going to be the beginning of the range plus the end of the range divided by 2. And then this is how we compute the variance. But let me show you real quickly. It'd be a good idea to get a good hold on what not only a uniform distribution is, a continuous uniform distribution is, but also learn about what it really means to be a continuous distribution by calculating these things ourselves. So let me head over to an example. Let's take the continuous uniform distribution in our case that takes on values between 1 and 6. This may seem similar to our die rolling example, but it's a little bit different, and I'll show you why. A continuous uniform distribution on the range of values 1 to 6 is going to look like this. There are no discrete in-between outcomes here. It's just a one big block. It looks like a rectangle where the height is constant across between 1 and 6, and it sits at 1 over 5 here. And now we said that the function for it is piecewise because it is 1 over b minus a for any x value that is in between a and b, and then it is 0 elsewhere. And that means, like, over here there is no probability density at this point right here because it is outside 1 and 6. And here there's no probability density because it's outside 1 and 6. And so essentially that means that no matter where you're at, no matter where you're at here, the height of this rectangle is going to be equal to 1 over 5 anywhere in there, because since this is the function right here, and b is 6 in this case, and a is 1, 1 over 6 minus 1 is 5. And so when we compute the expectation, I said that when we compute the expectation of a discrete random variable, we use a sum over all the outcomes multiplied by their probability. And so it's a weighted average of each outcome multiplied by their probabilities. And so when we do continuous random variables, we talk about doing integrals because we're summing over an infinite number of values within a particular range. And so the expectation changes from the sum, right? It's the summation symbol of x times p of x. Okay, it changes from that to this, the integral, okay, from a to b of x times f of x, and then dx. Right? And so this little dx right here, this isn't an integral calculus class, but I think it's important to note that this is the summation, right, is going over each possible outcome times the height at that particular outcome. And so the dx is just representing this. If you look over here, it's representing an infinitesimally small x, right? So beforehand we had discrete outcomes. We could just take this x and multiply it by its associated probability, and that's how we did the discrete random variable. But now we're dealing in terms of densities, and so we don't have particular outcomes, right? We have an infinite number of outcomes. So we want to figure out what it would take to be able to sum up, to compute the expectation of all these little infinitesimally small little slivers of outcomes. And that's what the dx represents. And if that doesn't make sense to you, please review an integral calculus course and learn more about integral calculus. You'll be able to explain it more in depth. As a matter of fact, the best way to understand that, how that dx sums up over an area, is sums up infinitesimally small slivers under a particular curve, is to look up the Riemann sum. The Riemann sum is the best way to understand that. If we wanted to calculate the expectation of this particular function right here, this distribution, over its range of values, it would be the integral from 1 to 6 of 1/5, which is the function itself. I'm switching up x and f of x, it doesn't really matter, times x dx. This is going to be 1 over 5 times the integral from 1 to 6 of x dx. And this is going to be 1 over 5 times the integral of 1 over 6 dx. What we're going to have right here is we're going to have, this is going to be x squared over 2, And then what we're going to do is we're going to integrate it from 6 to 1. And what this means is that we plug in 6 right here, and then we subtract off plugging in 1. Then we plug in 1 and we subtract it off. So it's going to be this, right? I'm going to write it out explicitly and then subtract it off. And this is going to be 36 over 2. And then this is going to be 1 over 2. So the inside right here is going to be 1 over 5 times 35 over 2. And these cross out, and this becomes a 7. And so this is 7 over 2. And it's going to be equal to 3.5. And that's the same expectation that we got whenever we did the 6-sided die roll, right? Where it took on values between 1 and 6, but they were discrete outcomes. Even though now it's a density and the height is different, we still get the same expectation. And because of, and the height's different just by the sake of how we define the uniform distribution function, how it's actually defined over the range of values 1 to 6. Same expectation, different height. That's a very interesting thing. I encourage you to think more about that. And so we're going to talk about the normal distribution. This is usually what we refer to as the bell curve. And this is a famous continuous distribution. It is a probability density function. And the function itself is just, the first time you see it, I wasn't even able to write it correctly on the slide, or at least in a readable format. But this is the actual function. And no matter whatever sigma and mu value you plug in here, it's going to give you, the density for all different x values. And so sigma is the standard deviation. It's going to determine how wide the distribution is. Mu is going to be the expected value. It's going to determine the central tendency, or the mean of this distribution. And you can plug in mu and sigma and everything else held constant, and then you plug in just an infinite number of x values, and then it will plot out this distribution that we commonly know as the bell curve. And so the expected value is mu, and I just said that the variance is sigma squared, but this is the standard deviation. And so let's actually look at how this would look like if you saw it, and let's explain some of these properties. And so if I'm looking at let's imagine we had a normal distribution. Okay, and then this side goes out to negative infinity, this side goes out to infinity. And let's just say that we had a normal distribution where the mu, okay, I can draw a better mu. Let's actually draw it down here. The mu is equal to 0. And the, let me move this down a little bit. And then the sigma squared, or the sigma, right, is equal to 1. This is our standard normal. What you're going to see is that what this is going to look like is you'll get this like distribution that'll sort of like rise around 0. It'll have its height at 0. And then it'll sort of, and that doesn't look symmetric, but maybe I won't be able to draw it perfectly symmetric, but essentially it'll have its height, right there around 0. It's not drawn perfectly. But this is the mean. The mean is the point where you have the highest hump in the normal distribution. Sigma is going to determine exactly how wide it is. And in the standard normal distribution, the density, 99.7% of its density, or area under the curve, it's just another way of saying it, is going to lie within 3 standard deviations of the mean. So within 3 standard deviations, you go, so this is 0, you go 1, 2, 3 this side, and then -1, -2, -3, and 99.7% of the density is going to fall within 3 standard deviations of the mean. And that comes to show you like why it's used. It's like it's got all of its density around its mean. It's a very nice curve, and it's used to model a lot of like real world phenomena. The function itself is it's a little crazy. I think it's a little wild, but For such a clean looking curve, it's pretty complicated to look at, but that's the normal distribution. That's what the mean of the normal distribution means, is how the standard deviation determines its width. If the standard deviation was a little bit smaller, like let's just say we move the standard deviation down to like 0.5, then maybe we would get a curve that looks like this. It's like a little bit taller, right? And it's got a little bit, it's a little bit skinnier, and the width is a little bit smaller. And then as you get, say you had a standard deviation that was like 3 and a little bit larger, maybe you'll have something that looks like this, it'll sort of change the way the curve looks, and so it has fatter tails, And so you change mu and you change sigma. Like if you were to change mu to like, let's just say 3, then maybe, and you kept sigma at 1, then it would just sort of shift this curve. It would shift this curve out here. And that is a little bit about the normal distribution and how the mu and sigma parameterizes it, changes its shape, can change its location.